Welcome to tutorial number 2, Tools and Techniques Useful for Creating a Mission Animation. If you're considering competing in NASA's Break the Ice Lunar Challenge, then this tutorial is especially for you. And if you're on the fence about whether to compete in this challenge or not, I think watching this tutorial will help ease some of your anxieties and apprehensions about creating the mission animation deliverable. If you haven't watched our first tutorial, please go do that now, because this second tutorial actually builds on that work. Tutorial 1 can be found on the challenge website, breaktheicechallenge.com, under Resources and Media. My name is Kurt Loit, and I'm a small part of the NASA Centennial Challenge's team of experts who've created NASA's Break the Ice Lunar Challenge. I'm a NASA software engineer focusing on robotic systems and other technologies that we might use in the future to support long-term human exploration of the moon.
Hi, I'm Tracy Prater, and I'm part of the team that created this challenge. I'm an engineer in the Materials and Processes Laboratory at NASA Marshall Space Flight Center, where I support projects related to 3D printing, in-space manufacturing, and planetary surface construction.
In this tutorial, Tracy and I will demonstrate a chain of utilities and tools that you and your team can use to create important elements of your mission animation.
We want to be clear that this is only one of many examples of tools that teams can use. Any tool or tool chain that you're comfortable using is perfectly okay and accepted by the rules.
That's right. We don't want to give the impression that we endorse certain tools and not others. That's simply not the case.
This simple flow diagram illustrates the chain of utilities and tools that we're going to demonstrate for you in this tutorial.
You'll recall that in tutorial 1, we showed you how to create a 3D model of the lunar surface. That will be our starting point for this tutorial.
We'll open the 3D model in a gaming engine and simulation tool called Unity. We'll use Unity to create a realistic looking 3D lunar environment that we can look around in and interact with in real time. And we'll even add some simulated lunar mining equipment on the lunar surface.
Then we'll turn that simulation into a game file that can be executed on your computer. Once the lunar simulation is running on your computer, we'll show you how to record your computer's display using an application called VLC.
If you have problems with or questions about any of the tools we're about to demonstrate, please don't contact the Break the Ice Challenge team. Instead, contact the appropriate tool vendor using the information on their website.
So, if you're ready, let's get started.
Unity is a very popular game engine that's free for personal use and also free for small companies. We'll use Unity to create a 3D simulation and a realistic looking model of the lunar surface, complete with simulated lunar mining equipment.
Yeah, but feel free to use any tool that you're comfortable with in order to create your team's mission animation deliverable. Unity can be downloaded freely from unity.com. All websites used in this video are included as links below the video for your convenience. From the Unity Hub app, click New, select 3D, and give your project a name and an appropriate folder location. Then click Create. We'll call our project Lunar Simulation, and we'll just put it on the desktop for convenience. Notice the default Unity project starts out with a sample or default scene, a main camera, and a directional light. It's super easy at this point to bring our 3D model of Shackleton Crater that we created in tutorial 1 into our scene. You'll recall that we saved that 3D model on our desktop with the file name of surfacescaled.obj. All we do is drag that file into our Unity Project's Assets folder, like so. Now we can simply drag it from there into our scenes hierarchy, and it's rendered in the scene window using the correct scale of about 20 kilometers across and about 4 kilometers deep. Let's zoom out so we can take it all in.
I did not think it would be that easy. This is amazing.
Yeah, simulation software and game development software have really come a long way, haven't they, Tracy? Our crater is being displayed as completely white, but we can create a material in the Assets folder by right-clicking and then hitting Create Material and give that material a name, like Surface. And all we do to pick a color is to click in this box, and we're going to choose a nice gray color for the surface of the moon. If we open up the surface hierarchy, we can see the mesh that makes up the surface, which has the name default. If we drag our surface gray color over this mesh, Unity will now display our surface in the gray color that we've created. Now let's adjust the camera inside our simulation. Because there's no atmosphere on the moon, we don't want our camera to clip the scene based on distance from the camera's lens. We actually want to see everything, no matter how far away it is from the camera. So let's select the main camera, and let's change its far clipping value to a very large number. 30 kilometers should do the trick. Let's move the camera way back here to the near rim, and we'll set it up to look out over the entire crater. This little preview window shows us what the camera can see whenever we have the camera selected in the scene hierarchy. Yeah, that's a pretty nice view of the whole crater. Right now, even though we've hardly done any work at all, we actually have a working simulation. We can preview our simulation by clicking the play button in the main toolbar, and Unity will now show us the live camera view in this window. We are right now looking at a live 3D simulation, even though nothing is actually moving in this scene. Well, not yet anyways. Click the play button again to stop the simulation and return to the scene design mode.
Wow, that looks great. But can Unity also simulate lunar gravity and lunar lighting conditions?
It certainly can. Teams can configure the gravity settings. They can configure the lighting settings. They can even create a skybox to simulate a star field overhead. These are more advanced topics that we don't have time to demonstrate in this video, but there are plenty of tutorials on the internet covering these topics, and many more. So get creative and make your simulation look as realistic as you like.
Can we add something that moves around in our scene, like a rover, for example?
Sure, it's pretty simple to add a mobile robot. We'll start by adding a simple placeholder object or stand-in object though. Let's move our design perspective around to the side of the camera. Let's create a simple 3D cube as a temporary stand-in for our rover. Right-click in the hierarchy, select 3D Object, Cube. If we drag this cube down toward the surface a bit, you can see that it intersects the surface at some point, and you can see the shadow underneath of it. Let's keep it hanging in midair for just a bit, and that'll make sense later. And just to make sure this cube stands out nicely in the 3D scene, we can make it a little bigger. That's simple. We just make sure our cube is selected, and then we modify the scale values right here under Transform. We can also make our cube nice and bright. It's quite easy to do. We just add a material to our asset folder by right-clicking, Create, Material. Let's choose a nice bright red color. Now we have a material that we can apply to anything we wish. Just drag this new red material onto the cube object in the hierarchy to apply it to the cube. Now if we select the camera in the scene hierarchy, we can see the cube from the camera's perspective in the camera preview window. It really stands out. Let's preview our simulation again. Yeah, we can definitely see the cube. You can tell by the shadow on the surface that the cube is floating in midair though. So let's add some physics so that the cube will act like a real 3D object. With the cube selected, in the inspector window, click Add Component, Physics, Rigid Body. Let's preview our simulation again. Almost. The cube definitely has some physics because it fell that time, but the crater surface didn't appear to do anything to stop the cube from falling. The crater surface needs a bit of physics too. So let's open up the crater surface objects drop-down in the hierarchy to see the actual underlying mesh. Select the surface's mesh. Then in the inspector window, click Add Component, Physics, Mesh Collider. Now, let's see how this all acts in the simulation. There it is. Now we have a simulated crater with a simulated 3D rover stand-in peering over the edge.
It's looking great. Why don't we drive this rover around in the simulation?
Yes, I agree, Tracy. It's a bit more work, but it is totally worth it. In order to give the human operator some control over the rover's motion, we need to create a very simple script. Now, I'm the self-proclaimed software geek, but creating a script to control the motion of a 3D object in Unity is not very scary, and it actually makes a lot of sense once it's done. And it's only 5 or 6 lines of code. So Tracy, do you want to give it a shot?
Yeah, I'm sure I can handle 5 or 6 lines of code. To create a new script for your simulation, right-click inside the Assets folder, click on Create, and then choose C# Script. Unity creates a new script file inside the folder. We'll want to give the script a name that makes sense. Let's call this script Rover Control. Unity lets you edit your script using any text editor or program environment that you like. I'm not a professional programmer, so I'm going to use the text editor Notepad for my script. This shows you just how easy it is to edit or create a script right within the Unity environment. All scripts used in this video are included as links below the video for your convenience. Unity gives you a good start for your script by creating a template that contains most of the required information. Before I type anything into my new script, it already has a class called Rover Control defined, plus a start function, plus an update function. This isn't that hard to understand. The class is just a container for the code. The start function will run when the simulation begins, and the update function will run every time the simulation refreshes the screen. Now we're going to add a line of code between the class and the start function. All this line does is set the speed of the movement of the rover. The word public allows the speed value to show up in the Unity user interface and allows the Unity developer to modify the speed value for this script without having to go into the code and change it there. It's pretty convenient. Now we're going to add some lines of code to our update function. So these need to be typed inside the white space between the curly brackets under update. These 2 lines of code just grab inputs from the player. In our case, we're going to be using the 4 arrow keys on the keyboard. These two lines of code are a little confusing, but all they're really doing is making the inputs from the user small enough to look realistic inside the live simulation. We're almost done. Just one more line of code. This line is what makes the rover move in three-dimensional space. We're only telling it to move in two of the three dimensions though. It will be able to move backward or forward and also right or left. What you can't do is make it go up or down like a helicopter, although that might be fun. Once you're done modifying your script, you just save it and go back to the Unity window. Unity will automatically check your script for errors, and it will tell you in the console window if it finds something within your script that it doesn't understand. How did I do?
I don't see any errors. You did great, Tracy. Now, can you show the viewers how to attach their new script to the rover stand-in object?
This is really cool. All we have to do to attach a 3D object, like a cube, to our new script is to drag the script from the Assets folder directly onto the cube in the project's hierarchy. It's really that simple. Now in the Inspector window, we can see that the rover control script is showing as being attached to our cube object.
Now we can run the simulation again and see how the cube reacts to our arrow keys. Arrow up, arrow down, arrow left, arrow right. Look at that! We can now control our stand-in rover and make it drive around on the surface of the moon. That's really great! But as I drive the rover away from the camera, it just gets smaller and smaller, and it'll disappear at some point. We need a way to make the camera actually follow the rover. There are lots of scripts on the internet that create all sorts of fancy player follow motions for cameras. But the simplest way to make our camera follow our cube is to just make the camera a child of the cube here in the scene hierarchy. Let's test it. This is fun. We're just driving down into Shackleton Crater now. I feel like I'm actually exploring the moon with a remote control rover.
I'll admit it, that was fun. But wouldn't it be more fun to drive around a 3D model of an actual rover rather than just a cube?
Yeah, I agree. Let's do that. Do you have a rover 3D model in mind that you'd like to use for this tutorial?
I would love it if we could drive NASA's newest Mars rover, Perseverance, around the moon in our simulation. NASA has a 3D resources website where we should be able to find a Perseverance model.
That sounds fun. Let's do that. Obviously, teams that are competing in the Break the Ice Lunar Challenge will want to bring in their own 3D models to show off and demonstrate their own mission architecture designs that they've come up with as their unique solution to the challenge. But just for the purposes of this tutorial video, I'm just going to go grab NASA's Perseverance rover model from the NASA 3D Resources website. It's nasa3d.arc.nasa.gov. Just click on 3D models, jump down to the models that start with the letter P, click Perseverance, and download. Once the file is downloaded, we can simply unzip it. Now let's look and see what exactly was inside that Perseverance zip file. It looks like it's a Blender model based on this .blend file extension, which means if I double click on this blend file, it will open up in the same Blender 3D modeling application that we used in tutorial 1. Once the file is opened in Blender, I can interact with it and zoom and rotate. The blend file actually describes a complex 3D system of objects, and this particular blend file even includes a timeline and animation commands, which makes some of these 3D objects move based on time. Let's move animation time to a spot where the rover is all unpacked and ready to explore the surface. Now we can simply export the scene as a wavefront OBJ, just like we did in Tutorial 1 for the lunar surface 3D object. We'll call this 3D model Perseverance. Now we can go back to Unity and we can drag this Perseverance OBJ file into Unity's Assets folder. Now we can just replace the temporary stand-in cube with this detailed 3D rover model. This time, let's drag Perseverance from Assets directly into the scene right next to the cube. And we'll fine-tune its position just a bit, and we'll make it floating just like we did the cube. Also, let's go ahead and make it red just like the cube so that it really stands out. If we start the simulation now, Perseverance will float in midair just like the cube did before we added the physics components. Now, let's add a box collider to the rover. And let's make it roughly match the size of the main chassis of the rover. Let's also add the physics rigid body component to the rover. When we start the simulation now, the rover falls to the surface resting on its chassis, which makes sense because that's where we created the box collider.
That rover looks amazing, but we're not just going to drag it around on its belly, are we?
That would make for a funny video, but it wouldn't be very realistic, which is what we're going for. So we're going to add some wheel physics. Adding wheels that interact with the surface isn't actually a huge deal. We just add 6 simple 3D cylinders as children underneath the Perseverance default mesh object in the hierarchy. And then we place them each in just the right spot to match the wheels of the detailed rover mesh. These 6 gray cylinders aren't very pretty to look at, but they can be used as physics collision objects, and we can make them invisible by turning off or removing the mesh renderer in the inspector window for each wheel. If we now swap the rover control script from the cube over to the Perseverance rover, we can actually make it slide around on the surface on its wheels, just like we did with the cube earlier. To remove that script from the cube, we just right-click on the script and remove component. And then we just drag that rover control script from Assets onto the new Perseverance object in the hierarchy. Whoops, almost forgot. Our camera is still attached to the cube. Now we're moving a detailed 3D model of Perseverance around on the lunar surface, and the camera is following along. Pretty amazing, especially for the small amount of time and effort we've spent on it so far. The only tweak we need to make is to the rover control script. It's written right now to just slide a 3D object across the surface without any control of its pointing direction, which isn't realistic for a wheeled rover. But with just a couple more lines of code, we can have proper and realistic control of our rover. If we treat the sideways control inputs as rotations instead of translations, we can drive our rover around properly. Let's see how it works now. That's much better. Yeah, this is pretty amazing. I could probably drive the rover around all day like this. Go explore, little rover.
I can't believe how easy this is, even for a non-software person like me. Let me ask you a question though. The camera that automatically follows the rover is a really fun point of view, but for my mission animation deliverable, I might want other camera angles. So besides the third person, or third rover as it were, what are my options?
Good point, Tracy. In Unity, you can set up as many cameras as you wish, and then switch between them inside your simulation using a simple script. If you really wanted to get fancy, you could even drive a camera manually in 3D space via the keyboard, similarly to how we drive our rover using the keyboard. Or you could even fly a camera through a programmed three-dimensional path using a script. But I'll show you a simple stationary camera shot. This camera shot is one of my favorites. If we move our camera in the hierarchy back to a stationary position, and then put it really close to the surface and also tilt it upwards a bit, we can get some cool shots of our rover driving right past the camera. This is what's called the beauty shot. She's a beautiful rover, isn't she? Or we can even drive our rover right on top of the camera, which is another pretty impressive camera shot.
This is going to create some amazing video footage. But what if I wanted several robots, each working independently inside my simulation? I only have 2 hands, so how would I control multiple robots using my keyboard?
Yeah, so far we've only demonstrated controlling a single robot using the arrow keys on the keyboard. If you wanted to crowd several people around a single keyboard, I suppose you could assign different sets of keys to different robots and control them that way. Although that might get a little crowded. Unity allows you to use joysticks too, which is a fun option. Once you get beyond just a couple of robots being controlled simultaneously though, you might want to graduate from manual robot control to automated robot control scripts. That's a more advanced topic that we don't have time to demonstrate in this video, but there are plenty of tutorials on the internet covering such things.
I feel like we now have all the tools we need to create an amazing lunar architecture. But how do we capture this amazing simulation footage in order to make a video out of it?
Good question. Once our simulation is completely developed and fully tested inside the Unity app, we can compile or build it as a standalone application. Just click File, build and run. Once you give it a location, and I'm going to just choose my desktop for convenience, Unity will compile everything we need into a file that we can execute or run. When Unity's finished building, it'll run the executable that it just built. Now that we have a standalone simulation app, we just need to record it in action so that we can create our mission animation deliverable. To record a video of our computer's display or screen, we'll use a tool called VLC.
VLC, otherwise known as Video LAN Client, is a popular open source desktop application that lets us record, stream, and convert video files. VLC is the last tool in our tool chain and will allow us to record our simulation.
Once you've captured all of your 3D simulation footage using VLC, you'll still need to edit that footage into a final mission animation video for uploading to the internet. We won't be demonstrating that in this tutorial, but there are plenty of tools and tutorials on the internet that teams can use if they're not already familiar with video editing technology. VLC can be downloaded freely from videolan.org. All websites used in this video are included as links below the video for your convenience. In VLC, choose Media, Convert/Save, go to the Capture Device tab, and select Desktop Capture Mode. Choose the frame rate that you want to record. Slower frame rates take up less disk space, but too low a frame rate will end up looking choppy. Also, the video editing software that you intend to use may require certain standard frame rates, like 30 frames per second or similar. VLC will record your entire desktop by default. If you need it to record just a portion of your desktop, it has a full set of command line options available. The command line options can be accessed by clicking Show More Options. When we click the Convert/Save button, it doesn't start quite yet. It needs to know the location and name of the video file that it's going to create, along with the type of file that we want to create. We'll choose MP4 as the file type. We'll put it on the desktop and we'll call it Video Capture 1. Now, as soon as we hit Start, it will begin recording our desktop screen to a video file. Now we can run the Unity executable that we compiled earlier. And we can perform whatever actions inside our running simulation that we want recorded. When we're all done capturing the action from our simulation, just switch back to VLC and click the Stop button. Now we should be able to play the video file that we just recorded.
Once a team has captured all the simulations and operations that they want to show off, they'll just need to edit those files together into the mission animation deliverable.
Well, that should give all teams and potential teams an idea of some of the tools and techniques they can use to create their mission animation deliverable for NASA's Break the Ice Lunar Challenge.
Thanks for watching this tutorial video. We hope this video is helpful for any teams considering entering the challenge.
Yes, and best of luck to all the teams who do enter. We can't wait to see all the novel and innovative solutions that each team comes up with for excavation of icy regolith at the South Pole of the Moon.
Bye!
Bye!